Okay, so before Thanksgiving break, we took a look at solving systems of equations using graphing. You guys see on page 135, and I'm going to flip back here for just a second. So we looked at problems where we had two equations, right? That's our system. And we graphed each line that was part of our equation. And then we looked at where they intersected. And that point of intersection, that point that was on both lines, is our solution to that system. So we looked at a lot of problems where we had a place of intersection. We also saw that we could have lines that never intersect. We have parallel lines, we would have no solution. And then we also looked at if we have lines that are actually the same line, one line graphed right over the top of the other one, said, or we knew that that meant there were infinite solutions, right? Every point on that line would be a solution since it's the same line right on top of itself. We also looked at, right before break, being able to create our own system of equations from a word problem. So we did that on Monday of last week. We looked at creating that system ourselves and then graphing those lines and looking for that intersection point. So we did one where we actually graphed it by hand. And then we had several problems where we wrote a system of equations and then we used our calculator to find that intersection point rather than graphing by ourselves on a coordinate plane on paper. This solution would be a difficult one to find exactly graphing on paper. So would this one. We've got such a large scale for that y that this could be a difficult solution to find graphing by hand. We'd used our calculators for some of these problems last week because it's not always easy to find the solution to a system of equations by graphing. We're going to take a look at some other strategies that we have to solve systems of equations. So the beginning part of this week, we're going to look at some other algebraic options that we have to solve systems of equations. Today, we're going to start by looking at what's called the substitution method for solving systems of equations. So here's the big idea if we want to use substitution to solve the systems of equations. So the first thing I need to do is pick an equation and get one of the variables by itself. So get x or y by itself in one equation. It doesn't matter which equation you pick. It doesn't matter which variable you pick. I'm going to encourage you to make choices that make the work easier on yourself, but you can solve any system of equations by substitution by solving for either variable in either equation. It doesn't matter. Just some of those options are going to be easier than others. Then once you have a variable by itself in one of those equations, you're going to substitute what that variable is equal to into the other equation, okay? So we'll take a look at this. So substitute, that's called the substitution method. Substitute into the other equation and solve for a variable, that remaining variable. So if we take a look at the first problem here on this page, if I cover up everything past the x, this is a problem similar to what you guys looked at in middle school, right? You said, I have this expression, evaluate it when x equals 2. So you would take 2 and plug it in for x in the expression and see what you got, right? Simplify. We're doing the same thing here. So we're going to take this value of x and substitute it into this other equation. But now, instead of just simplifying that negative 3 times 2, we actually have another variable that we need to solve for. So this is a system of equations where one of our equations is just an x equals a number, right? So still a system, this would still give us a line, right? A vertical line where x is 2. And then we're looking at where would that intersect with this other line, okay? So since this guy, this top equation, already has x by itself, That means that I want to go ahead and use this and plug this value in for x in my other equation. This is a substitution strategy to solve this system of equations. So I have negative 3 times 2. Since x is equal to 2, I'm plugging that in for x. I'm substituting that in for x plus y equals 12. Now I want to simplify anything I can here. So negative 3 times 2 would be negative 6 plus y equals 12. And then I want to get y by itself. So I want to move this 6. To move it, I have to add 6 to both sides, and I get y equals 18. So now I know what x is equal to, and I know what y is equal to. So I know the solution to the system. Just like before break, we're going to put our solution into an ordered pair, x comma y. My solution is 2 comma 18. So if I looked at the graph, that would be the place on the graph where the coordinates, where my two lines intersect. Questions for me on this first example? Okay, now I'm not always going to have a value stated for one of our variables. So let's take a look at this next problem down, where I do have one of my equations that already has a variable by itself, but this time I don't know the value for x. I just have a different expression for x. So I've got x by itself in this top equation. It's equal to y plus 3. So what I'm going to do is take this y plus 3 and plug it in for x in that second equation. Same idea, just this time I don't know what number x is equal to quite yet. So this would be 2 times y plus 3. Instead of x, I'm plugging in y plus 3 minus 3y equals 4. I want you to notice that everything about my equation is the same, except instead of x, I have y plus 3. Everything else is the same. And now I want to simplify and get y by itself. Here's the big idea behind substitution. We've had an equation that had two variables. When I've got two variables, I can get one of them by itself, or we could have gotten the y by itself if we moved the 3 to the other side. But the problem is, up here, even when I have x by itself, I still don't know what x is equal to. So I have this y hanging out in here. If I rewrite an equation so that it only has one variable, now I can actually figure out what that value will be, okay? Because I can get y by itself. That's the big idea here. We take an equation with two variables that we're kind of stuck with, and we rewrite it in a way where we only have one variable, and we can actually solve for that variable. So as I put to solve for this variable, I've got to distribute this 2 inside parentheses. That would be 2y plus 6 minus 3y equals 4. I'm going to combine my like terms here. 2y minus 3y would be negative 1y plus 6 equals 4. Now I want to get that y term by itself, so I'm going to subtract 6 from both sides. So I get negative 1y equals 4 minus 6 is negative 2. And then my last step to get y by itself, I've got negative 1y right now, and I want just plain old y. I'm going to divide both sides by negative 1. So I get y equals 2. Negative 2 divided by negative 1 is 2. Since I only had y's here, I could solve for y. Now that I have y, I can use that to be able to figure out x. So I'm going to take y now and plug it into one of these original equations. It doesn't matter which one, but if I plug it into the top one, remember we're trying to solve for x. Now that we know y, we're going to plug in that value to solve for x. This guy has the x by itself. if I plug it into the second equation, I've got a little more rearranging I'll have to do. You can plug it into either, but I'm going to choose to plug it into the one that's going to give me a little bit less work. So this would be x equals 2, and that's our value for y, 2 plus 3. So x equals 5. So our solution here is 5, comma, 2. Questions on this one? Okay, let's hop down to the last problem in this column. For this system, we don't have either equation that has a variable by itself. None of these is set up ready for me to go with substitution. That means I'm going to have to rearrange one of them so that I can use substitution. So of these equations, we'll call this top one equation 1 and then the bottom one equation 2. Which of them looks like it would be easier to get a variable by itself? Probably the top one, right? You could get x or y by itself in the bottom equation, but you're gonna, if I wanted to get x by itself, let's say, you would have to move the y term and then divide. Same if I wanted to get the y by itself, I'd have to move the x term and then divide. So I've got 2 steps to get a variable by itself for that bottom one. For the top one, I only have to move the thing I don't want, okay? So since we had x equals for the last couple, let's get the y by itself this time. So that means I need to move the x. So I get y equals 4 minus x. 1 step to get a variable by itself. And now I can go ahead and use my substitution. So I'm going to plug this stuff in for y in the second equation. So I have 2x plus 7 times 4 minus x equals -2. I'm going to distribute inside those parentheses. So I've got 2x plus 28 minus 7x equals -2. Combine your like terms. 2x minus 7x is -5x plus 28 equals -2. I want to get the x term by itself, so I'm going to move that 28 to the other side. So I get -5x equals -30. And now my last step to get x by itself, divide both sides by -5, and we get x to be 6. So I found x. Now we're going to go back and find y. So I can plug this x value into either of my original equations, or we could plug it into this sort of rearranged first equation. The nice thing about plugging into that rearranged first equation is that y is already by itself. So when I plug in that value for x, I don't have any rearranging to do. So I get y equals 4 minus 6. That gives me y equals -2. So my solution would be 6, comma, -2. Questions on our third example? Okay, let's hop over to the top of that second column. I don't have a variable really by itself right now. Which one might be a good equation to work with to get our variable by itself? Why the top one? Yeah, so we only have x up here, right? If I move that 1 over and get x by itself, I have my value for x. Now I can take this value for x and plug it into my second equation. So -2 times 4 plus y equals 13. -2 times 4 is -8 plus y equals 13. And then we want to move that 8 to the other side, get y by itself. So I'll have to add 8 to both sides. And then get y equals 21. So my solution is 4, comma, 21. I want you guys now to try this middle problem in the second column. Give that one a shot. My second equation already has x by itself, so I don't have to do any rearranging here. I'm just going to take this stuff, this y minus 1, and plug it in for x in that top equation. So I have 2 times y minus 1 plus 3y equals 28. Now I'm going to distribute that 2 inside parentheses, so I get 2y minus 2 plus 3y equals 28. I'm going to combine my like terms. So 2y plus 3y is 5y minus 2 equals 28. Now I want the y term by itself, so I'm going to move this negative 2 to the other side. I can move it by adding it. Now I've got 5y equals 30. And to get y by itself, I'm going to divide both sides by 5. So we get y to be 6. Now that I know what y is, I can plug that back into either of my original equations. But again, you want to kind of work smarter, not harder. It'd be a little bit easier, a little bit less work for me if I plug it into that second equation. So x equals 6 minus 1. We get x to be 5. So my solution is 5, comma, 6. Any questions on this one? Okay, we have one more example on this page, this problem down at the bottom. Again, in my second equation, I have x by itself, so we're going to take this stuff, 3y plus 1, plug it in for x in that top equation. So we've got 3 times 3y plus 1 plus 4y equals negative 23. Distribute. So 9y plus 3 plus 4y equals negative 23. Combine like terms. That would be 13y plus 3 equals negative 23. Move the 3 to the other side by subtracting. And we get 13y equals negative 26. Last step to get y by itself here, we want to divide both sides by 13. And we get y to be negative 2. Now that I know what y is, I'm going to plug that back into one of my original equations. Again, I'm going to pick the equation that's going to be a little bit easier for me to solve for x. So x equals 3 times negative 2 plus 1. 3 times negative 2 is negative 6. So x equals negative 6 plus 1. That means that x equals negative 5. So my solution here would be negative 5, comma, negative 2. Questions on our last example on page 135? Okay. I want you to hop to page 137 for me. We're going to take a look at number 5. So similar to last week, we've got a word problem here, right? We're going to have to write that system of equations ourselves. But this time, instead of graphing on our calculator, we're going to go ahead and solve by substitution. Now, when we were writing systems that we were going to graph on our calculator, I stuck with X and Y as our variables because we were going to have to type them in our calculator, and our calculator only understands X and Y when we talk about graphing. Since we're not typing this into our calculator, you can use whatever variables you want and not have to worry about remembering, is this the X value, is this the Y value? It doesn't matter. We're not going to graph it. Okay. So for number 5, we're ordering baseballs and softballs for Little League. Baseballs cost $2.75 and softballs cost $3.25. We know that our total for 80 balls was $245. How many of each type did we order? So we ordered some baseballs, we ordered some softballs. We know how many total balls we got and the total cost. So I'm going to let B stand for the number of baseballs that we ordered. And I'm going to let S stand for the number of softballs that we ordered. I know that I ordered 80 total balls. So however many baseballs plus however many softballs came out to be 80 total things. So there's my first equation. And then the other bits of information I know are all about prices. So I'm going to write another equation incorporating those prices. I know it cost me $2.75 for every baseball that I bought. So 2.75 times B for however many baseballs I bought. And I know that it cost me $3.25 for every softball that I bought. So 3.25 times S. So 2.75 times B gives me the total cost of all the baseballs. 3.25 times S gives me the total cost for all my softballs. If I add those amounts together, I get my bill, how much I spent on all of these things, which we know is $245. So there's my system of equations. And now I want to solve this using substitution. So that means one of these equations, I'm going to have to get a variable by itself. Would we rather solve for a variable in equation 1 or equation 2? What do you think is going to be easier? Yeah, probably equation 1, right? I could solve for B or S in equation 2. But again, I want to sort of choose the path of least resistance here. What's going to be easier for me to be able to do? Probably get a variable by itself in equation 1. Okay, so B and S would be equally easy. I'm going to go ahead and get B by itself by subtracting S from both sides. So I would get B equals 80 minus S. And now that I have B by itself, I can plug this in for B in my other equation. So this would be 2.75 times 80 minus S plus 3.25 S equals 245. And now I've got some bigger, maybe stranger numbers for this system than we had for our other examples, but I'm still going to treat this the same way. So I'm going to distribute inside parentheses. 2.75 times 80 gives me 220. If you were working through this problem on your own and needed your calculator for that multiplication, that's fine. And then 2.75 times S, negative 2.75 S plus 3.25 S equals 245. Now I'm going to combine my like terms. Negative 2.75 S plus 3.25 S would be positive 0.5 S. So we've got 220 plus 0.5 S equals 245. I want to get that S term by itself, so I'm going to move the 220 over. That means subtract 220 from both sides. And we get 0.5 S equals 25. Now to get S by itself, I have to divide both sides by 0.5. So 25 divided by 1/2, that would actually be the same as 25 times 2. So we get S to be 50. So there's our value for S. Now I want to take this number and plug it back in to find B. Now remember, you can plug it into either of your original equations or this rearranged first equation. I'm going to choose to plug it into that rearranged first equation because that'll be a little less work for me to solve for B. So B equals 80 minus 50. So I get B equals 30. Now for this problem, since we have a context, I'm not going to give my answer as an ordered pair. Okay. Instead, I'm going to state what I know, right? The question was, how many of each type of ball did you order? I ordered 30 baseballs and 50 softballs. That's my solution to that system. Questions for me? Okay, so your homework is page 136. You have 4 systems to solve with substitution, and then finish up that last problem on page 137.